all this theory I have just told you looks too sophisticated, and I know that it's hard to understand all this without any example. So let's now try to solve an example and to have more practical look at this concept of hypothesis testing. So let's start with this simple example. Let's say that we have a coin, and the coin was flipped 1,000 times, and there were, let's say, 486 tails. So 1,000 flippings. And of these, 486 are tails. So the question is, can we say that the coin is fair? So we want to test a hypothesis that the coin is fair. As you see here, initially a hypothesis is not a statistical hypothesis. So we know that statistical hypothesis is a kind of a supposition about some random variable or some random variables. But we don't see any random variable there. They ask, so can we say that the coin is fair? We don't see any random variable here, any parameter distribution, and so on. So the first step I have not mentioned before is to translate the hypothesis we have from the human language to the mathematical language, to the language of the probability theory. So what can I say here? I can say that when I have a number of flippings of a coin, this is a series of Bernoulli trials. So I have a series of 1,000 of Bernoulli trials, and this 486 is number of successes in this series of trials. See, if we assume that tails is a success, so this is number of successes. So what can I say? I can say that initially we have observations. We have 1,000 observations, and they are all binomially distributed with parameters 1 and p. So xi is the result of the ith flipping. And so in each flipping we have either tails or heads. And so if ith flipping ends in tails, so the xi is equal to 1. And if in heads, then xi is equal to 0. So all these observations are ones or zeros depending on what happened, heads or tails or heads. So that is why we can interpret each of these random variables as a binomially distributed with parameters 1 and p. So each of these x's is a number of successes in a series of just one single trial. So that is why we have 1 here. And p is a probability of success, probability of getting tails. So p is the probability of tails. So, and when we say that we want to test a hypothesis that the coin is fair, that means that we want to test a hypothesis that this P is equal to 1/2. That probability of getting tails is equal to 1/2. Fair coin means a coin that gives us with probability 1/2 tails and with probability 1/2 heads. So our hypothesis is equal to the suggestion, to the supposition that this P is equal to 1/2. So that is why, that is how we can translate our initial hypothesis from the human language to the mathematical language. So, okay, is this hypothesis simple or composite? It is simple, as it is, it contains an equality. So, this hypothesis about the fairness of this coin is a simple hypothesis. So, as it is simple, it will be the null hypothesis in our problem. So, the null hypothesis is that P, probability of success, probability of tails, is 1/2, 0.5. So, what about the alternative hypothesis? Actually, standard practice is this. So, if the hypothesis that we are asked to test is a simple one, then we adopt this hypothesis as a null hypothesis, and then we are to choose its pair, to choose an alternative hypothesis. And in this case, the alternative is just a complement event. So as the null hypothesis is P is equal to 1/2, then alternative is P is not equal to 1/2. If the hypothesis we are asked to test is a composite hypothesis, in this case, we adopt it as an alternative one, in spite of the fact that actually this was the initial hypothesis we were asked to test. We adopt it as an alternative one, and then we choose a simple one to accompany it as a null hypothesis. But this is not our case, so in our case we have got just a simple hypothesis, and so it is very easy to formulate an alternative. It's just the not the null hypothesis. So equal, not equal. So this is our pair of hypotheses. Now we are to choose the significance level. So let us say that we choose standard significance level and that alpha is 0.05. So we have no arguments, no ideas that are in favor of choosing some other value of the significance level. So now what about this proposition? So that if the null hypothesis is true, some random variable, some statistic follows some distribution. So I told you that in all hypothesis testing problems, we have a theorem, a proposition of this kind. So how about this problem? So here we can just formulate this kind of proposition ourselves. So we know that if our observations are just zeros and ones, so then their sum total number of successes, total number of tails, is a random variable that is binomially distributed with parameters 1 and p. With parameters, 1000 and p. So we have 1000 trials. So number of tails, let's say that capital T is the number of tails. And number of tails is number of successes in a series of 1000 trials. So 1000 Bernoulli trials. That is why it is binomially distributed. Not equal, but it is distributed binomially with parameters 1000 and p. And our hypothesis is that p is 1/2. So if our hypothesis is true, if the null hypothesis is true, then t is binomially distributed with parameters 1000 and 1/2. So, and this is the proposition we are looking for. So if HO is true, then T has binomial distribution with parameters 1000 and 1/2. So if HO is true, we can substitute 1/2 for P in this expression. So this is the proposition. But actually, we can use this one. It is almost almost acceptable to continue using this proposition as the basis of our test for this hypothesis. But we know that it is usually very inconvenient to deal with a binomial distribution with a very big number of trials. When the number of trials is very big, we usually say that according to the de Moivre-Laplace theorem, we can say that we can use the normal distribution instead of binomial one. So we can say that as n is equal to 1000 is big enough to apply the de Moivre-Laplace theorem. We can assume that T is actually normally distributed, that T has normal distribution with parameters 1000 times 1/2 and 1000 times 1/2 times 1 minus 1/2, that is also 1/2. Or we can say that another random variable, T tilde, that is equal to T minus 1000 times 1/2 divided by the square root of 1000 times 0.25. So this random variable has standard normal distribution, normal with parameters 0 and 1. So this is the final formula of our proposition. So if HO is true, then T tilde has standard normal distribution with parameters, so normal distribution with parameters 0 and 1. So now we are to construct the acceptance region and the critical region for this hypothesis. So we will need quantiles of this distribution, of standard normal distribution, but we are to find, so what is the configuration of critical region? So do we have two-tailed critical region, or we have just one-tailed, left-tailed or right-tailed, left-sided or right-sided critical region? So how we can find this? Actually, it depends on the alternative hypothesis. So let's have a look. So if the null hypothesis is true, then number of tails is close to 500. So this means that for a fair coin, average number of tails when we have 1,000 flippings is close. Average number of tails is 500, and so actual number of tails is to be close to 100, not far from 500. So that means that this difference T minus, so 1,000 times 1/2 is 500. So this means that this difference T minus 500 is to be close to 0. So the value of the test statistic is to be close to 0 when the null hypothesis is true. So if this is true, this is to be close to 0. If P is not equal to 1/2, if the null hypothesis is false, if the P is more than 1/2, so probability to get tails is more than 1/2, then average number of tails is more than 500. And this difference is usually positive. And so the more far this probability is from 1/2, more positive this T tilde is. So if, for example, this is a very unfair coin and probability of getting tails is, for example, 0.8, this means that average number of tails will be 800 and the average difference here will be 300. So approximately 800 here minus 500, 300. So if P is more than 1/2, then this difference and the value of the T tilde is usually positive. For the same reasons, if P is actually less than 1/2, values of T tilde are usually negative. So what does it mean? If we think that if the alternative hypothesis, if it were not P not equal to 1/2, but P greater than 1/2, In this case, we would say that big values, positive values of T tilde are in favor of alternative hypothesis. If the alternative hypothesis were P less than 1/2, then we would say that negative values of T tilde are in favor of the alternative hypothesis. And so as we have an alternative hypothesis with not equal sign, so alternative hypothesis allows both probabilities more than 1/2 and less than 1/2. So in this case, we can say that both positive and negative values are of T tilde, so big positive values and big negative values are in favor of the alternative hypothesis. And so this determines the tail of the critical region. So if we say that only positive values of T tilde are in favor of alternative hypothesis, then we have right-sided critical region. If we say that only negative values of T tilde are in favor of the alternative hypothesis, then we say that we have a left-tailed critical region. And if, as we have in our case, if we say that both positive and negative values of T tilde of the test statistic are in favor of alternative hypothesis, in this case we have two-tailed critical region. So, critical region, tail of the critical region depends on the alternative hypothesis. If we have not equal, then we have two-tailed critical region. If we have greater sign here, we have right-tailed critical region. If we have less sign here, we have left-tailed critical region. So now let's apply this. So let me rewrite the main things. So T tilde is T minus 500 divided by the square root of 250. And we know that if HO is true, then T tilde has standard normal distribution. And so we now know that we have a two-tailed critical region. As we have a two-tailed critical region, so we need two quantiles of this distribution. So this distribution is what we called the law distribution in our theory. And so this is the alpha, the significance level. And so as we use the Z, letter Z for the quantiles of the standard normal distribution. So this is Z alpha over 2. As alpha is 0.05, this is Z 0.025. And this is Z1 minus alpha over 2. This is Z 0.975. And so these are two critical regions. And this is the acceptance region. Using the table of the quantiles of the standard normal distribution, I can find that this is minus 1.96 and this is plus 1.96. Actually, quantiles of the standard normal distributions are symmetrical. So quantiles of the level alpha over 2 and 1 minus alpha over 2 differ only in sign. So this is negative, this is positive. If the level of the quantile is less than 1/2, it is negative. If more than 1/2, it is positive. The quantile of the level 1/2, the median, is 0 for the standard normal distribution. So, and now let's calculate t tilde, the numerical value of t tilde. T tilde is t, that is 486 minus 500 divided by the square root of 250, and this is approximately minus 0.89. So t tilde falls into the acceptance region. T tilde is equal to minus 0.89. What does it mean? It means that we accept the null hypothesis, or in other words, we fail to reject the null hypothesis. So we can say that we accept HO at 0.05 significance level. So this is the answer. So now we are to translate it back from the mathematical language to the human language. So the null hypothesis is that P is equal to 1/2. P is probability of getting tails. So in other words, the null hypothesis is the hypothesis that the coin is fair. So how can we answer the question we were asked? So can we say that the coin is fair? Yes, we can. At the 5% or 0.05 significance level. So can we say that the coin is fair? Yes, we can. Yes, we can at 0.05 significance level. This is the only correct way to answer this question. So if we say yes we can, this is not true. So because we are limited with these possibilities of type 1 and type 2 errors. So we accepted the null hypothesis, but maybe we have just made the type 2 error. Type 2 error is to accept the false hypothesis. So maybe this hypothesis is not true, maybe it is false, maybe the coin is not fair, but we have just accepted this hypothesis. And so if we say just yes we can say that the coin is fair. We won't explain this situation completely. So we are to say that yes we can at 5% significance level. That means that there is a possibility of type 2 error. So, and this 0.05 is the probability of type 1 error, probability of false positive. So the probability of type 2 error cannot be calculated precisely, but so this phrase, so when we say at 5% significance level or at 0.05 significance level, we let people know that so this is not we are not, we don't know whether the hypothesis is true or not. We just say that our observations are in favor of this hypothesis, in favor of hypothesis that the coin is fair.